Hello, hello. We are finishing up this unit on solids and liquids today. And on Thursday, there will be a quiz followed by review stuff on Friday. And the test should be then a week from today, next Monday. So we ended the last session on Friday talking about the different types of crystals. So be sure you've thoroughly studied ionic, covalent, molecular, metallic crystals, and you could tell me about their general properties like relative melting temperatures and what forces hold them together, and could even give me some examples of each one of them. So we had previously talked about liquids, and so today we're going to talk about those transitions between solids, liquids, and then even to gases, because that will be our last chapter together. But before we move on to that, we're going to look at some applications we can uh, take if we have a crystalline solid. Remember, if we said if it's a crystalline solid that the atoms are lined up or molecules in a repeating pattern trillions of times over. And if we want to know whether it's simple cubic or rhombohedral or hexagonal or some other unit cell, then what we can use is a technique called X-ray diffraction. Now, if you want to see atoms, you're going to be kind of out of luck with a microscope because you can only resolve with a microscope down to the wavelength of light we're using, which if we're talking about a light microscope, which you look through and see visible light, then that means you can really only get down to about the 10 nanometer and or sorry, not 10, the 400 nanometer, and that's too big to be able to see molecular atomic things. And so instead of using visible light, we can use a higher energy wavelength like X-rays. And so this leads us to X-ray diffraction. Diffraction refers to how light scatters when it passes through a material, kind of like light passing through a prism white light can produce a rainbow. That's diffraction. And this is also sometimes called X-ray crystallography because it requires a crystal. So when you hear crystal, it has a crystalline, highly repetitive pattern. And so the way we can figure out about atomic structure is from shooting X-rays into a crystal, and the X-rays will then scatter. Now, there's some fun trigonometry that goes into this, but a father-son duo, William Bragg and William Bragg Jr., they worked out Bragg's law, which tells us how these X-rays scatter. And so what that means is we can take a crystal, we can shine X-rays and look at the diffraction pattern, and if we can figure out where it's diffracted, we can figure out where the electrons are, because the electrons are what are scattering the X-rays. And if we know where the electrons are, we know where the atoms are. And so we can work out an atomic resolution, uh, pretty much mapping of an atom, a molecule. So again, it's not like it's a type of microscope where it zooms in further, but it allows us to visualize in a way where how the atoms are arranged next to each other. And so if in the previous chapter, we talked about single bonds being longer than double bonds, which are longer than triple bonds, or when we talked about the bond angle between waters about 105 degrees, then it's X-ray crystallography or X-ray diffraction that's enabled us to be able to determine those geometries and lengths. Now, besides looking what small molecules look like. It's this heavily utilized in biochemistry and biology to determine biomolecular structures. One of the most famous comes in the structure of DNA. If you were to ask most people who discovered or determined the structure of DNA, the double helix, you know, 99 out of 100 people who know the story would say, oh, it's Watson and Crick, James Watson and Francis Crick, because they were, in fact, the ones who won the Nobel Prize for it. However, there was a third character. This is Rosalind Franklin. Now, she was not a collaborator, but she worked in a different lab trying to tackle um, the same idea of trying to figure out what is the structure of DNA. And so there was kind of this race going on trying to figure out what is the true structure. And this is her X-ray diffraction photograph of DNA. Now, there's some controversy. It's a pretty uh, there's a lot of details to this story, and I'm not going to go into a lot of them. I think I have a link below that talks about it. But Rosalind had this picture, and she was still trying to figure out the structure of DNA, and so did Watson and Crick, who were using different techniques. And one of her collaborators, without her permission, allowed Watson and Crick to get a view of this photo at a conference that they were attending that she was not present at. Um, and what it allowed them to do was pretty much confirm or isolate out of several theories that they had that it had to be a double helix, because they know from looking at protein structures that you only get this X pattern when you have helices. And so a lot of people think she should have shared the Nobel Prize with them for providing that data, but she happened to die the year before it was awarded, and they do not award the Nobel Prize post mortem. So that's fun. Also, proteins have been discovered, or not just discovered, but their structures being determined. There's this huge, if we're talking biology and biochemistry, and we want to know what is the function of a protein or how does it work, then structure is key. And so this is the first protein, myoglobin, which is very similar to hemoglobin that you find in your blood, but it was the first, first structure of a protein at the atomic resolution scale. And since then, hundreds of thousands of different proteins have been had their structures determined and cataloged. And so if a drug company wants to make a drug that would inhibit a certain protein, then this is the type of research they would need, or data they would need, to be able to figure out what would fit into its active site to essentially turn it off or on. And then here's a fun video you should definitely watch on celebrating crystallography. Again, this is either called X-ray crystallography or X-ray diffraction. Crystallography because you have to use crystals, and diffraction because then that's what the X-rays are doing as they pass through the crystal. So on to the last part of this chapter, a phase. Now you know this term. A phase is what type of matter we're seeing. There's three main phases: solids, liquids, and gases. Uh, um, Probably the next most one common you hear about is a plasma, which is essentially an ionized gas. Because one of the properties we'll talk about gases in the next chapter is that there are no intermolecular forces between them. They act independent. But if you're at such high temperatures that the gases are ionized, then electrostatic attractions can still have them push and pull on each other. And so plasmas act a little different. We're not going to cover that in detail, or actually any more detail than what I just said. So we're only worried in these three. There's also a few other obscure ones like the Bose-Einstein condensate it's not really essential or necessary for us to even talk about, so we're not going to. So and some of the properties, you already know these, but just be sure you know that gases, like this, I think we talked about this like in chapter 1 last semester. Gases take up the volume of their container, where liquids and solids have a definite volume. Gases or liquids and solids, again, they are incompressible, where gases are very compressible. And this goes back to their relative motion. Again, in the next chapter, we're going to talk more about the motion of molecules in something called kinetic molecular theory. But we refer to liquids and solids as the condensed phases, as in with density, and gases are the non-condensed. So there's some terms I want you to know, which you probably know most of them. Again, starting with a solid at coldest temperatures, we said there's only these local vibrations, and particles, they're packed together very tight and rigid. But now they have vibrations, they can shake and move, but there's no translational motion where one particle would move and shift past others. Now, if you put enough energy in, then solids can melt into liquids. I bet you already knew that term, melting. And then liquids can freeze into solids. So liquids have this kind of medium order where particles are still held together, but they're not tightly bound. So they can slip and slide past one another. They're just but they're not free to just wander off. Liquids can then vaporize to a gas, or gases can condensate. Condensation is going from gas to a liquid. And as a gas, that's where they're the most energetic. And this is where particles are completely separated from one another. Again, our last chapter will be about this phase. But again, these are the condensed phases, and this is the non-condensed phase. Now, the two other changes you might or might not know: sublimation, straight from solid to gas. If we were in class, I would show you some iodine, because if you take solid iodine and heat it up, it doesn't vaporize, it sublimates very easily to a gas, and it gives off a nice purpley color. And also we would watch this video on snowflakes, because snowflakes are an example of deposition. So water vapor in the atmosphere, crystallizing, which you, instead of condensing and freezing, it goes straight from a gas to a solid. And so snowflakes are an example of deposition. This is actually the way they make synthetic diamonds. So there's two types of diamonds you could buy. You could buy the really expensive ones that were formed deep in the earth, and then volcanic activity had spewed them up, and then they get polished up and people put them on jewelry. Or you could take high pressure carbon dioxide in an oven with a tiny slice of a diamond, and the diamond seed serves as a nucleation site where other carbons from the carbon dioxide will deposit onto the diamond, and the diamond the tiny sliver of a diamond you put in there will then grow and grow, and so it's a synthetic diamond. And there's rules that say for some reason you can't actually use them for jewelry, but if you want to have, if we're talking about like diamond tipped drill bits or diamond tipped blades and all sorts of things for industrial purposes, then they're typically using synthetic diamonds. Now, when it comes to vaporization, going to the gas phase, there's two ways this can happen. Um, the first, or regardless of the way, vaporization is going to the gas phase, but it does not. Normally, we think of reaching a boiling point, but this doesn't have to happen. So you do know that things can evaporate, and you spill water on a counter, and the water, it'll sit there for a while, but in a couple days it'll be gone. Now, it's not because it reached 100 degrees Celsius. It's that over time, thermal energy from the surrounding was pulled in to the water, and as the water absorbs more thermal energy, more molecules get enough energy to break their intermolecular forces and vaporize. But we call this evaporation when it happens below the boiling point. This is super important in the Earth's water cycle. It's the Earth's natural form of distillation. We talked about distillation as a way to purify all sorts of mixtures by separating them by boiling point. Well, if we didn't have evaporation, then all our water would be salty, and we wouldn't like that. Um, so again, remember the water cycle where you have the ocean evaporate, the hot sun gives some energy to the water. Water evaporates, it condenses, it precipitates, and it flows around and round and round and round. And so we're a big fan of that. Temperature regulation. It's also how we stay nice and cool. Perspiration. When we sweat, we normally think of that as a bad thing, but it's our body's way of dealing with the heat. So when you perspire, you've probably, again, if you've ever exercised and got all sweaty and then stepped in front of a fan, how icy cold the fan feels. That evaporation is a cooling process, so it literally has to take energy from you for the water to go to the gas phase. And so as it evaporates, it cools you off by taking energy, and that's very nice of it. You also probably know that in the summer, evaporation rates go up. So, at higher the temperature, the more energy to break intermolecular forces. And so, in the summer, if you spill a couple drops of gasoline while pumping your gas, it'll probably be gone within a minute. Whereas if same thing with water on a hot day. But in the winter, if you spill something, it can stick around for a while. Uh, Now, there's enough, we typically only think of temperature as how we get things to vaporize, but another important variable is the pressure. So pressure is essentially the force dispersed over an area, and equilibrium vapor pressure refers to the force of particles vaporizing off of a liquid. So in this scenario, imagine we have liquid water vaporizing to a gas, but at some point the gas is also going to condense down to a liquid. So imagine we have this setup where this is a piece of ice put in a glass jar, and when all of it, not ice, just water, when you first put it in there, water is going to be vaporizing away, and you have just vaporization. But over time, there will be more and more water vapor in this system, and you'll start getting some condensing. And eventually you're going to get to a point where the amount vaporizing is equal to the amount condensing. And that's why we have these double arrows here. It's showing that this is a reversible process. So you can boil water, and then water vapor steam can condense. So when these two rates are equal, we call that an equilibrium. So the rates are equal. Now it doesn't mean the rates are zero. So if you have a bottle of water and you noticed with the cap, if you left the cap off, in a couple days the water level would have gone down because some of it would have vaporized away. But if you leave the cap on, then that water is going to stay in there indefinitely. Now that doesn't mean it's not vaporizing. It doesn't mean there's no evaporation. However, as some of it is vaporizing, some of it is also condensing. And so at equilibrium, there's just no net change. Now, if we're talking about sodas, again, keeping your soda nice and fizzy is all about keeping pressure to combat the CO2's vapor pressure. So the worst thing you could probably do to keep your soda bubbly is just leave the lid off, because then CO2 will just keep coming out and coming out and coming out, because it's not going to reach this equilibrium, because it would take a whole lot of CO2 in um, the universe to equal that out. That's not going to happen. So at the very least, you put on a lid, and as soon as enough vaporizes that the external pressure is equal to the vapor pressure, and you reach the equilibrium, and you won't lose any more fizz. Additionally, you could purchase the Fizz Keeper. You can buy one of these at Walmart. I've never actually used it for this intended purpose, but essentially you screw it on, you pump air in, and so when you increase the vapor pressure outside of it, you increase the amount of the gas that stays inside. And you probably imagine you have your fizzy drink and you release the cap. What happens to the liquid? You automatically see it bubbling, and you see it bubbling because with less pressure up here, then the vapor pressure, then it's allowed to vaporize. So it's the vapor that kind of holds the gases in. Now, again, going back to pressure, we can talk about the boiling point with respect to that pressure. We typically think of boiling, at least water, at is 100 degrees Celsius. Um, but what's significant about that number is that just happens to be what the vapor pressure would be when at sea level for water. So if you're at a low temperature, there's very low vapor pressure of water. As the temperature increases, the vapor pressure of water or any other liquid increases and increases and increases. And as this chart is showing, It's in terms of millimeters of mercury. Um, all you need to know is that happens to be 1 atmosphere. So this is what you're feeling right now. And so as the vapor pressure rises with temperature, evaporation rates go up. Well, boiling doesn't kick in until the vapor pressure is equal to the external pressure. So once it hits this mark, notice at 1 atmosphere of pressure, that's when it boils. Now, what's significant about that is if you change the external pressure, you change the boiling point. So if the pressure drops, the boiling point goes down as well. A couple places we can see that is cooking at high altitudes. So at high altitudes, there's less air, and that means there's less pressure. So as the pressure goes down, it means water doesn't have to get to as high a temperature for its vapor pressure to equal that. And so if you cook something to boiling at high altitude, you'll find it takes longer because the water doesn't get to as high temperatures. Cooking's all about putting in energy, not necessarily how hot it gets. So the higher temp you cook it at, the more energy gets put into it. And since boiling point goes up as pressure increases at high altitude, it's the opposite. Pressure goes down, so the boiling point goes down. So again, here's a graph of altitude. So at 0 degrees, this is in Fahrenheit, so water boils at 212. But if you go up 1,000 feet, 210, and then lower and lower and lower. So if you go to the top of Mount Everest, um, then water boils at 160 degrees. Now, what that means is, even though if you started if you started boiling water, it would boil faster because it only had to get up to 160. So, but then when you try to cook something, it will take longer because it's cooking at a lower temperature. Now, in contrast, a pressure cooker allows you to reach higher pressures. So it seals it off, and because it will get up above 1 atmosphere, the external pressure gets higher, then it takes longer for the vapor pressure of water to reach it. And so they can reach up to 250 degrees Fahrenheit. So if you want to cook something fast, you cook it at higher temperatures. And in this case of boiling something, you can use a pressure cooker. I recommend watching this video on the Leidenfrost effect. It's that phenomena. If you've ever dropped water on a hot skillet and it just dances all over, it's a pretty neat phenomena, and it just talks about it. The last thing in this chapter is the phase diagram. So we now know that boiling and melting, we know that they're temperature dependent, but those temperatures are dependent on pressure. And so all of the different phases get condensed into this chart where we have 3 different phases: solid, liquid, and gas. And it shows the different ways that you can have melting or condensation or sublimation, deposition. And so we have all of these different ways we could go across this thing. So the lines represent the boiling curve. So at 1 atmosphere, water boils at 100 degrees Celsius, and it freezes, or sorry, it melts at 0 degrees Celsius. And technically, the melting point and freezing point are exactly the same, just like the boiling point and condensation point are exactly the same. And then what this also shows is if you lower the pressure, then you come across this line, it changes the melting point and it changes the boiling point. And then it also shows what it takes to sublimate. Sublimation is, if you've ever heard of freeze-dried food, if you've ever had astronaut ice cream, it's kind of like a chalky, milky something. Then it undergoes what's called lyophilization. And so they have like a milk suspension, but to get rid of the water, they first freeze it and then they dry it. So the freezing component, that's shown here in this arrow, is they cool it down in liquid nitrogen. And by bringing the temperature down, it crosses the freezing point and you now have a solid. Now, typically when you dry something, we think about heating it up. but instead they put it under a vacuum. So in a essentially something that pumps the air out and makes the pressure go really, 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 really low. And so when it does that, when the pressure drops, eventually it passes this sublimation point mark, and the water it lyophilizes or sublimates away, and you're left with something that has similar shape, but it did not go through the melting process. We also find here this is the triple point. So technically at every point it is an equilibrium. So the boiling point is an equilibrium between vaporization and condensation. The melting point is an equilibrium between melting and freezing. Well, where all three of these phases come into to interact, this is called the triple point, and this is where all three phases, sublimation, deposition, melting, freezing, condensation, boiling, all of these can happen at the exact same time, and it's kind of a weird thing. Now, you don't typically see this for water because its triple point is at 0.006 atmospheres, and that's pretty low. This is cyclohexane. Its triple point is much higher, so it's a lot easier to actually get there. Now, the triple point also tells you, how can I make something sublimate? Because for sublimation to happen, the pressure has to be below this triple point. So for water, that's why it has to get put in a vacuum so that it goes at 0.006. If we were to look at the phase diagram of iodine, I mentioned it normally sublimates, and its triple point is much, much higher. Here's a look at carbon dioxide. So in dry ice is called dry ice because when you hold it in your hands, and it might hurt for a second, it doesn't get your hands wet because it naturally goes straight from a solid to a gas because it has a really high triple point of 5 atmospheres. And so at 1 atmosphere, it just goes straight from solid to a gas. To get liquid CO2, you'd have to pressurize it past 5 atmospheres. Again, so here's hexane, here's iodine, um, and so all of these, again, they have, these values change depending on the substance. Oh yeah, and there's the whole thing. So yeah, dry ice normally is going to sublimate. And that's the entire chapter. I hope you enjoyed it. I did not enjoy it as much as I normally would because this is a fun chapter because there's lots of stuff to show. We missed out on a dry ice lab where we would make a dry ice bomb and explode it safely and other things. But anyway, there's quizzes and tests coming up. Please be sure to do the homeworks. And when you take a quiz or test, after you hit submit, go back to Google Classroom and hit turn in. I get a lot of emails that say it says it's missing. It says it's missing because you didn't turn it in. There's nothing technically to turn in. Turn in just means, hey, you did it. And that way it won't say missing for you. So anyway, have a great Monday.